Advanced Ceramic Nanocomposites. Lection 2. Synthesis of nanocomposite ceramic powders. In this lecture, we will discuss the next synthesis method of nanocomposite ceramic powders. Mechanochemical methods, polymer precursors methods, vapor phase methods of synthesis, self-propagating high-temperature synthesis, sol-gel synthesis, precipitation, solution combustion, spray decomposition methods, and surface modifications route. The simplest method to make nanoparticle in the form of powder is milling. Planetary vibration, rod timbre, controls the speed of rotation and duration of milling grip material. To find powders, some materials like tungsten, cobalt, chrome, etc. are made nanocrystalline using ball mill. Most ceramic composite powders are currently synthesized via mechanochemical mixing of their constituent phase. These methods involve a meticulous selection of raw materials with a keen focus on factors such as primary particle size, size distribution, agglomeration, degree, and purity. The attainment of high purity powders in the imperative or circumvent the formation of secondary phases during the sintering process. A broad particle size distribution, while leading to higher packing densities in green bodies, possess challenges in controlling microstructural development during sintering. This is due to the potential coarsening of larger grains, including smaller ones. Furthermore, the particle size plays a crucial role in determining final grain size and densification rate. As the particle size decreases, the specific surface area increases, consequently enhancing the densification rate. Moreover, when a powder exhibits a certain degree of agglomeration, the packing in grain density becomes heterogeneous, resulting in different sintering rates and heterogeneous microstructure. But sintering we will discuss in the next lecture. Here we will discuss mainly the synthesis methods, but with point of view of the next step of consolidation, these nano powders. As mentioned, the mechanical milling is the easiest way to obtain nanomaterials and dispersed materials. The one of these methods, the variation of this method is mechanochemical synthesis, when mechanical reactions take place. Mechanochemical synthesis involves the effective mixing and of reactants through ball milling, either without or with only a minimal amount of solvents. This approach is not only ensures efficient synthesis but also conserves energy and time. Consequently, mechanochemical processing is esteemed for its environmentally friendly or green nature. Mechanochemical synthesis involves high-energy milling techniques and is often conducted under controlled atmosphere. It has been successfully employed for complex composition and for materials like aluminum oxide reinforced with intermetallic compounds. This method is versatile, embodying the preparation of composite powders for oxide, non-oxide, and mixed oxide, non-oxide materials. According to fracture mechanics theory related to high energy, milling can produce fragments of range from 5 to 100 nanometers. However, it's common to observe particles as small as 100 nanometer in ceramic milling tests. Instead, larger particles containing ultrafine grains and typically generated. Additionally, in situ localized phase transformation have been observed in response to localized demand during milling. Despite its advantages, mechanical synthesis has drawbacks. It struggles to produce discrete nanoparticles in the finest size range, and there is a risk of powder contamination from the milling media, especially with extensive and repeated milling cycles. Mechanical synthesis methods are solid-state processing that constitute an alternative to those based on the use of liquid solvents. Mechanical methods have potential for industrial use as they are simple, scrapable, and environmentally friendly. The solid-state reactions in mechanical synthesis can be used to obtain nanoparticles with small size and well-controlled crystallinity at very low cost. Herein we report on the mechanical synthesis of titanium oxide. We can find reports about mechanical synthesis of titanium oxide photocatalytic nanoparticles with controlled particle size and crystallized structure. As reported, Dinda and colleagues hydroxyapatite after 2 hours of high energy ball milling in an ambient atmosphere completely transformed into nanocrystalline powder from initial reagents. The crystalline size of all 6 powders mixtures was found by authors to be in the range of 18 to 20 nanometers after 1 hour and between 20 to 23 nanometers after 2 hours of milling. The next techniques to produce nanopowders with different structure is solution combustion synthesis. It's a popular bottom-up techniques are the wet chemical producers such as solution combustion synthesis technique, solution-based hydrothermal and solvothermal methods for polyol synthesis methods. However, the production of different nanostructures on a large scale through these techniques is currently limited due to the difficulties in controlling the properties of the bulky materials and the utilization in some cases of non-environmentally friendly chemicals. Additionally, the high temperature synthesis of some metal oxides makes this procedure expensive at industrial scale. The solid combustion synthesis technique is a relatively new material manufacturing method, accompanied by a robust high temperature and self-sustained exothermic reactions that makes this technique a highly energy efficient process. Herein summarize the surging popularity of solution combustion synthesis techniques. This method employs a homogeneous aqueous mixture of precursors followed by condensation to form a hydrogel containing a homogeneous metal cations network. The combustion reaction takes place between an inorganic reagent, generally nitrates, and fuel upon calcination. Regardless of operation mode, all combustion synthesis requires an external heat source to ignite the combustion or redox precursor mixture. Each route involves a specific methods of combustion synthesis. The typically adopted method is to place the ceramic container containing the precursor solution on the hot plate or inside the preheated furnace at 300-500 Celsius. Heating will cause in the solvent and evaporate from precursor mixture and lead to the formation of hydrogel. The hydrogel then decomposes and self-ignites, followed by combustion, and then produce a solid product like this. In subsequent steps, as you can see on this picture, the different nanostructured could be synthesized using these methods like nanoparticles, nanoplates, etc. The next one is polymer precursor route. Polymer-derived ceramics is an alternative and conventional powder-based ceramics. Here, a pre-ceramics mostly in silicon-based polymer, e.g., for example, polysiloxane, polysilicon, or polycarbosilicon, is used as starting material. The cross-linked polymer can be transformed into a ceramic material by controlled thermal decomposition. Treatment, so-called pyrolysis. The first step concerns the preparation of polymeric precursors, pre-ceramic, so-called pre-ceramic polymers, by incorporating the desired chemical groups. A second optional step consists in shaping the polymer via different techniques, as listed in this slide, depending on the target ceramic shape which has to be given. Sacrificial templates may be used during this shaping process to develop the porosity in the final material. The conversion of the polymer into a ceramic can be operated in different ways using different curing pyrolysis technique. Another way to proceed to the shaping is to first synthesize fine-grained polymer-derived ceramics powders and to shape them afterwards before a sintering treatment. The great advantage of polymer precursors route lies in its so-called bottom-up approach. The synthesis of the various ceramic always starts from a molecular precursors commercially available or homemade, which is subsequently polymerized by reacting with the linking agent or and through thermolysis, leading to a polymer we define as pre-ceramic. Before polymerization, the molecular precursors can be modified by incorporating of other elements into its chemical structure or mix with another molecular precursors. The confers a huge versatility to this approach and uh, allows a large variety of composition and structure to be generated after pyrolysis, influencing greatly the properties of these ceramics. Here you can see some example of nanostructured obtained via polymer precursor route. For example, pyrolysis of polymer precursors was performed under nitrogen atmosphere at 1400 centigrades, resulting in the formation of silicon-boron carbonitride fibers. These fibers was obtained by Bernard and colleagues via polymer precursors route. These fibers have an average diameter about 23 micrometer were obtained by this method. The fibers exhibit a tensile strength around 1.3 GPa and Young modulus around 172 GPa. The ceramic fibers retained their amorphous character until 1700 centigrades. And using these techniques, we can it's a possibility to obtain not only micron size materials, but the materials with quite lower size. For example, using this route in could be using this technology, it's a possibility to form composite fiber nanomaterials. For example, we in the Institute of Material Science in Ukraine, the Fratsevich Institute of Material Science, was synthesized the silicon nitride nanofibers as intermediate product for producing composite materials. The silicon nitride nanofibers covered by titanium nitride nanoparticles as intermediate product for producing titanium nitride. Previously, we synthesized on the silicon nitride fibers the oxyhydroxide of titanium in the presence of urea. The titanium hydroxide is presence of atropine and titanium peroxide hydroxide. Titanium oxyhydroxide that was obtained by thermal hydrolysis of titanium chloride in urea solution is placed on amorphous silicon nitride fibers. After the nitriding step in ammonia flow, we can cover the silicon nitride fibers by titanium nitride nanoparticles. According to transmission electron microscopy, there are fine titanium nitride particles formed during chemical synthesis over silicon nitride nanoparticles. The diameter of silicon nitride nanoparticles was around below 100 nanometers, you can see it, and the nanoparticles of titanium nitride, which was synthesized on the surface of silicon nitride nanofiber, was around 20 nanometers. This process may be used to make a nanocomposite base on refractory compounds reinforced with nanofibers. Titanium nitrate over silicon nitride fibers will promote the compaction of nanocomposite. The strength, fracture toughness, and high temperature hardness of these materials would improve as well. And we will show it in next lectures. The next methods of synthesis is so-called gas-phase processes. One of these processes is plasma chemical synthesis. Gas-phase processes are environmentally beginning as they are not connected to liquid influence. The cleaning of liquid influence is difficult and costly. In addition, because the synthesis of nanopowders is in most cases connected with a low concentration, the amount of solvents needed in processing huge. Powder synthesis based on reaction in a gas phase is based on purely random process for particle formation. In general, this leads to a broad distribution of particle size, in some cases, variants of these processes, to the formation of particle clusters. There are applications where broad particle size distribution and clustered particles are disadvantageous. To solve these problems, many process variants and nuances in processing were developed. A broad group of gas-phase processes is connected to plasma. A plasma-containing particle is called dusty plasma. Particle synthesis is always connected to a dusty plasma. There are additional possibilities to exploit the repelling phenomenon between the particles. The most attractive one is coating with the second phase. This second phase may be a ceramic or polymer one. Coated nanoparticles like this are of special interest with respect of their physical properties. On the one hand, a coating acts as a spacer-reduced interaction of a particle's property, which is important, e.g. for magnetic particles, and on the other hand, coated particles allow to combination of different properties in one particle. In plasma, it's possible to synthesize different materials, especially for high melting point from high melting point compounds like some nitrides of refractory materials, carbides, borides, etc. And the advantage of these methods is possibility to produce big batches of nanopowders. The next techniques is laser process of nanoparticles synthesis. In general, plasma process driven by lasers may be subdivided into two groups. A laser ablation process working with solid targets and laser process working with gaseous targets. Here you see the laser ablation process. This process have in common that the beam of laser is focused on a spot. The intensity in the focus is so high that a gas phase is ionized. Plasma is formed and responsible for the further progress in reaction leading to particle synthesis. Also, for this process, a wealth of literature exists. However, it is possible to extract a few characteristic design features. In the laser ablation process, a intensively laser beam is focused onto a surface and a target like this. The target may be a poor metal or oxide or even a mixed system. Because of the high energy input coming from a pulse laser, the material of the target is vaporized instantaneously. This process preserves even a stoichiometry of complex mixed target in the vapor phase. The intense electrical field of the laser beam ionized and vapor. The supersonic jet is evaporated material. A plume is ejected perpendicular to a surface of target. The temperature in the plume reaches volume values of 3800 Kelvin and more. During the adiabatic expansion of the plume, the temperature decreases and as the vapor gets supersaturated particles are nucleated. Within the short time interval of supersaturation, the particles are formed. Here you can see some examples of particles which obtained by laser ablations and the process how to obtain the nanoparticles using the technology of laser processing. But it have to be mentioned that not very compared with other plasma technique, these materials we can produce not very big batches of nanoparticles. The next technology how to synthesize the materials is the self-propagating high-temperature synthesis method. Using this method, it's a possibility to form of controlled combustions to proceed controlled combustion synthesis and is now utilized extensively in many countries. But being relatively new, it will be briefly introduced here. Self-propagating high-temperature synthesis exploits a highly exothermic solid flame reaction between powder components and components to produce a large range of unique materials by controlled high-temperature combustion. It was first introduced by Merjanov in 1967, but only now it stay worldwide. It's the end of 19th. Using self-propagated high-temperature synthesis, compositions, structure and property of the material can be tailored to satisfy requirements of many applications. Initiation of combustion takes place either by chemical route or an electrically heated element. Once initiated, combustion is self-sustaining and proceeds by a combustion wave sweeping through the compacted material from the initiation side to the opposite side, and is completed in the time of few seconds to a few minutes. The specimen here you can see how combustion, the ignition, and how combustion wave from one side to the other side expands. The specimen can be either at room temperature or preheated to a relatively low temperature, rarely above 1000 centigrade. The material on front of propagation wave is preheated by heat generated by combustion, and the material behind a combustion front is rapidly cooled as the wave sweeps past it. A schematic diagram of self-propagated high-temperature synthesis showed here, and the basic principle of this synthesis could be formulated as the next. The first one, rapid afterwave combustion like self-sustaining reaction yielding resultant products to desired combustion and structure, composition and structure. Uh, the next one, complete or partial elimination of external energy supply by utilization of the internal heat realized in the chemical reaction. And the last one, controls the process rate, temperature, degree of conversion and composition and structure of products by variation in the rates of heat realized and transfer. After ignition, the reaction travels as a wave through the pellet, exothermically converting the reactants into products as it propagates. In this case, the products are formed as discrete ceramic particles, for example, like titanium carbide, aluminum oxide, silicon carbide, and other. As observed, the reduction of combustion temperature when adding diluents correlates to a reduction of average particle size of the final products. Here you can see how the time influence in this reaction for the material during self-propagating cell high temperature synthesis. The next technology very popular is the Zolgale process. It's a more chemical method, so-called wet chemical method, for the synthesis of various nanostructured, especially metal oxide particles. In this method, the molecular precursor, usually metal alkoxide, is dissolved in water or alcohol and converted to a gel. Um, by heating and stirring by hydrolysis, alcoholysis, since the gel obtained from the hydrolysis alcoholysis process is wet or damp. It should be dried using approximate methods depending on the desired properties of application of the gel. For example, if it is an alcoholic solution, the drying process is done by burning alcohol. After drying stage, the produced gas are powered and then calcinated. The Solgel method is a cost-effective method, and due to the low reaction temperature, there is a good control over the chemical composition of the products. The Solgel method can be used in the process of making ceramics as molding materials and can be used as a intermediate between thin films and metal oxides in various applications. The materials obtained from Solgen method are used in various optical, electronic, energy, surface engineering, biosensor, and pharmaceuticals and separation technologies such as chromatography. The Solge method is a conventional and industrial method for the synthesis of nanoparticles with different chemical compositions. The basis of Zolge method is production of a homogeneous solg from precursors, its conversion into a gel, and solvent in the gel is then removed. The solvent in the gel is then removed from the gel structure, and the remaining gel is dried. Here you can see it. The properties of the dried gel depends significantly on the drying method. In other words, the removing solvent method is selected according to the application in which the gel will be used. Dried gel in various ways are used in industries such as surface coating, building insulation, and the production of special clothing. In this work, mentioned in that by grinding the gel by special mill, it is possible to achieve nanoparticles. The process of inorganic polymerization or salt gel method is an inexpensive, low energy consumption, and stable processing for obtaining high purity ceramics, which offer versatility of the production of different kinds of devices. The production of ceramic nanofibers, here you can see it, with high porosity makes the surface area even greater, with the successful results in most cases of application. Avila Martinez and colleagues produce a material of zirconium oxide obtained from the salt gain methods using zirconium butoxide as a precursor mixed with polyvinyl pyrrolidone and electrospun into fibers for the capture of allura red dye. Average fibers diameter range from approximately 100 nanometer to 300 nanometers. Here you can see some examples of different fibers. The titanium nanoparticles were obtained using Zolgel method and deposited on a top of silicon substrate, then covered with a thin film of gold and annealed. In order to form the gold nanoparticles, the substrate was tested. The Prakashan at Codex produces ceramic matrix composites with silicon oxide, titanium oxide, and argentum. And it's possible to synthesize it not only with argentum nanoparticles, with zirconium dioxide nanoparticles. It was made specifically for deflection of vitamin A. The next technology is dissolution method, so-called the co-precipitation techniques is becoming increasingly important to distribute material and precursor used in reaction to produce required materials. The aim in so-called co-precipitation is to prepare multi-component material through the formation of intermediate particles, usually hydroxide and oxalates, so that an intimate mixture of components is formed during the precipitation, and chemical homogeneity is maintained on calcination. In the typical process of co-precipitation, aqueous materials aqueous metal salts are mixed at sufficient temperature with a base, which acts uh, as a precipitating agent. This method is widely employed in a synthesis. However, in a few cases, the process is performed under inert atmosphere. The advantage of the coprecipitation method is that it gives a crystal size in the smaller range. Here you can see it's quite below 100 nanometers. Compared to the other synthesis processes depending on the precipitation and accelerating during the sintering during the reaction. In principle, dissolution of solid into liquid or other solvents is a process by which the original states become dissolved components, solutes, hence forming a solution of the solid in the inorganic solvent. When a dissolution occurs, the dissolved component separates into ions or molecules, and each of them is surrounded by the molecules of solvent. Using the dissolution process, one can generate a precursor of cation from a metal or mineral if it's soluble in a selected exit. The pure magnesium oxide, titanium oxide, zirconium, silicon oxide, nanopowders could be produced by this method. The main step for the metal case was the formation of precursors and appropriate calcination temperature. So-called drying. For the mineral case, purification of phase under consideration by reacting the contaminating phase with acid or base, followed by filtering, washing, and calcination, was the key of the process. As you can see, it's quite fine particles could be synthesized using these methods. And the last one is so-called ion implantation method of nanoparticles synthesis. Ion implantation is a material surface modification process by which ions of a material are implanted into other solid material, causing a change in the surface physical and chemical properties of the material. On implantation was developed as a method of production of p-n junction of photovoltaic devices in the late 1970s and early 1980s, along with the use of pulsed electron beam for rapid annealing. Also, pulsed electron beam for rapid annealing has not yet been used for commercial production. Ion implantation is not used in most photovoltaic silicon cells. Instead, thermal diffusion doping is used. When dopant ion strikes the substrate surface, it penetrates into substrate crystal matrix to a depth that proportional to its energy and angle on incidence. It doesn't penetrate the substrate in a linear manner, but rather takes a Dankart's walk pass through the crystal as the direction scattered. So like this. By collision with the substrate atoms. The use of ion beams to modify the surface of metals and alloys have been available as a research tool for several decades, but it was only towards the end of the 20th century that the techniques found widespread implementation for commercial products. Other than for a very high value added components such as racing car engine components and knee joints. Unlike its widespread use for some semiconductor processes, it has been the high initial capital cost of equipment coupled with the long process times that has held back exploitation despite the overwhelming evidence of property improvements such as for wear and corrosion application. The underlying concept behind ion implantation is simple. A beam of ions from any source is accelerated at various voltage and allowed to impinge upon a special surface such as that the ions interact with that surface and some are embedded in it. The beam can either be static, broad, and unidirectional, or a fine beam can be passed through the mass spectrometer to isolate specific isotopes that can be rastered over a sample surface. The latter can give very precise results in terms of specific dosages and areas covered, whereas the former requires employ equipment for all of large areas, for example 1 square meters, to be implanted at the same time. The success of ion implantation process is heavily dependent on the quality of the vacuum within ion implanters. Here you can see some example of formation of nanograins in the under the surface treated using the techniques of ion implantation. In addition to the present method of sintering of ceramic nanopowders, there are other methods you can find in literature. Sometimes there are solutions for the synthesis of nanocomposite powders involving several methods, or even innovative ideas how to produce desired nanopowders take place. The main task at this stage is the synthesis of powder of necessary dispersion and scale with the orientation towards the further application of consolidation method. The consolidation methods we will discuss in the next lecture, and thank you for your attention.